knows a lot about the science stuff. Professor Dave explains.
Throughout this series on particle physics, we've learned about the Standard Model. We talked about the building blocks of the model, both the particles and the forces, as well as the underlying theory behind them. We also touched on some of the shortcomings of the model and how they manifest within the discrepancies between theory and experiment. For the next few tutorials, we'll go through a brief overview of some of the ideas that are currently being proposed and experimentally sought, in an attempt to improve and expand the Standard Model. Scientists know it is an imperfect model, and they're constantly working to test it and find out which theory can explain its imperfections. Since this material will be on the cutting edge of modern physics, it may quickly become outdated as new discoveries are made. But this is exciting. It means the field of particle physics is alive and well, and ready for more eager and inquisitive minds to join the quest for knowledge about our universe. First, let's talk about unification theories. Known within the Standard Model, there is an electroweak phase transition. As we previously discussed, at a certain point in the history of the universe, the electromagnetic and weak forces were unified into one interaction. Some physicists go a step further and propose the idea of a grand unified theory, in which the electromagnetic, weak, and strong forces are all unified at some high enough energy scale. This has several fascinating implications, but the main one is that quarks and leptons are not necessarily distinct. If there is a grand unified theory at some scale, then quarks and leptons must be related in some capacity, which would indicate that they could turn into each other on large enough timescales. This would suggest that proton decay is possible, and it is no longer the completely stable particle we thought it was. Experiments like super-kamiokande and DUNE are able to place limits on the decay lifetime of protons and help test if a grand unified theory really could describe our reality. Now let's go one step further. What if the fourth force, gravity, was united with the other three? String theory aims to do this. By proposing that the point particles in the Standard Model are actually vibrating strings, the theory is able to create a quantum description of gravity. Within string theory, there is a massless spin-2 boson for gravity called the graviton. This is one of the most sought-after unification theories in all of particle physics. String theorists often craft theories involving many extra spatial dimensions, and lots of exciting new physics can emerge from this string-based reformulation of spacetime. However, the math behind these ideas could be an entire series on its own, so we won't go into more detail here. String theory currently has only minimal empirical backing, but many labs around the world are awaiting the opportunity to look for validation of string theory's predictions by refining our understanding of particle interactions and gravitational effects. Switching gears, you may remember from a previous tutorial that there is violation of charge parity symmetry that appears within the Standard Model. Unfortunately, the amount of CP violation that Standard Model processes can account for is not enough to explain the current asymmetry between matter and antimatter in our universe. There are two main ways that scientists are searching for CP violation: the electron electric dipole moment and the neutron electric dipole moment. If a particle has an intrinsic electric dipole, that means its positive and negative charges aren't perfectly on top of each other. That alignment violates both P and T symmetries, and by the CPT conservation theorem, implies CP violation. So finding a non-zero EDM would be direct evidence of CP violation. The electron EDM can be searched for with polar molecules which have strong electric fields that would amplify any signal from an electron EDM in experiments like ACME and other work at JILA. Currently, the upper bound on the electron EDM was set by ACME2 at around 10 to the negative 29. The neutron EDM is tied to QCD, since the neutron is a constituent particle made up of quarks. In QCD theory, there is a parameter theta that should violate CP. Since we do not see large CP violating effects within the strong force, this theta term must be very small. This is known as the strong CP problem, and observation of a neutron EDM could help determine what theta is and help solve this mystery. The leading effort on neutron EDM is the N2-EDM experiment in Switzerland. However, there are other ways to solve the strong CP problem, as we'll discuss when we talk about axion-like particles. Next, let's talk about the way that colliders like the LHC at CERN are searching for physics beyond the Standard Model. Before the LHC was turned on, many physicists were excited by the idea of supersymmetry. This is the theory that every particle in the Standard Model has a supersymmetric partner. A superpartner would correspond to each Standard Model particle, and it would have a spin that differs by 1/2, as well as a different name. For fermions, an S is added to the front of the Standard Model particle name, and for bosons, an ino is added to the end. For example, the photon superpartner would be the photino with spin 1/2. The quark superpartner would be the squark, and the electron partner would be the selectron, both with spin 0. Unfortunately, when the LHC was completed and started taking data, no evidence for supersymmetry was seen. To this day, some are still using the LHC to search for signs of supersymmetry. One might then wonder, how is the LHC used to search for anything? The Large Hadron Collider is exactly what the name suggests, a collider of hadronic particles that is large. Using magnets and other electromagnetic tricks, beams of protons or heavy ions are accelerated and bent so that they travel at very high speeds around the collider's circular path. Then, the beams are directed so that they smash into each other. There are 4 main interaction points between the beams, and at each one lies an experiment: ATLAS, CMS, ALICE, and LHCb. When the beams collide at an interaction point, the constituent QCD parts of the particles are broken apart. For heavy ion beams, this turns into a very high-energy primordial soup known as quark-gluon plasma. This plasma is short-lived and quickly replaced as QCD effects take over. For proton beams, particle showers are created that shoot outwards in jets. The detectors study these momentary collisions and can obtain valuable physics information from both the particles and energies present in a jet, and the missing energy from the collision carried off in particles that escape detection. Shortly after the LHC began operation, the ATLAS and CMS collaborations discovered the Higgs boson. This was the first instance of the LHC, allowing physicists to build and expand on the existing framework of the Standard Model. Electroweak symmetry breaking predicted a Higgs boson, and the LHC pinned down its mass. Then, thanks to experimental confirmation of its existence, many new theories were developed across particle physics. Specifically, with the Higgs, it is likely that it can interact with itself and other particles in new ways, including rare decay paths. These provide insight into the mechanism that gives mass to some Standard Model particles. Additionally, the LHC is looking into a plethora of other physics beyond the Standard Model. LHCb is exploring the universality of lepton flavor within the Standard Model. CMS, ATLAS, and ALICE are searching for exotic particles, including bound multi-quark states, with up to 6 or more quarks, and other unique quark interactions and pairings that could tell us more about how QCD behaves. They're also searching for long-lived particles and other theoretically motivated particles that would expand the Standard Model and could partially explain some of the dark matter in our universe. On top of all this, they're constantly coming up with new ideas and new ways to probe the Standard Model. At the LHC, among the 4 experiments, there are currently more than 10,000 collaborators who are all playing a role in testing the Standard Model and searching for new physics to add to it. Through some of the ideas discussed here, and many more, they are all trying to improve our understanding of the particles that make up our universe.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.